Estimating concrete quantities is an important part of the construction process. It's crucial to make sure the material estimates are spot on. If we go overboard and overestimate the materials, we have to go through the hassle of moving them to another site or storing them, which means more labor and higher costs.
Our objectives for today are:
1. We need to be able to describe metric, linear, and weight conversions. 2. We need to be able to explain how to use denominant numbers to calculate area and volume. Lastly, we need to be able to define square measurement. Numerous nations across the globe rely on the metric system as their primary measurement system. The majority of goods these days bear labels featuring metric units alongside their English counterparts. That's why it's crucial to feel at ease with the metric system. In the metric system, the fundamental measure of length is the meter. Any measurement greater than a single meter is just a multiple of the meter. So when we talk about a kilometer, we're actually talking about 1,000 meters. The entire metric system is based on the number 10, making unit conversions a piece of cake within the system. To switch 1 kilometer to meters, you multiply 1 by 1,000. So 1 kilometer equals 1,000 meters. Likewise, to convert a meter to centimeters, simply multiply by 100. So 1 meter turns out to be 100 centimeters. Translating measurements from one system to another needs to be handled with great care. Equivalency charts can be put to use to help you convert a measurement from one system to its equivalent in the other. However, you may need to do some math to finish up the conversion. In the English system, 1 meter equals 39.37 inches. 1 centimeter equals 0.3937 inches. And 1 millimeter equals 0.03937 inches. When dealing with English measurements that involve fractions, the initial step involves converting the fraction into its decimal representation. Subsequently, this decimal value is multiplied by the conversion factor. It is highly beneficial for craftsmen to acquire proficiency in utilizing conversion charts. The craftsmanship approach to weight measurement in the English system is built upon the concept of a pound, which consists of 16 ounces. In the realm of the metric system, weight is measured using grams as the fundamental unit. 1 pound is about 453.6 grams. Denominant numbers refer to numerical values that are associated with units of measure. Examples of such measures include inches, centimeters, feet, yards, and kilograms, as well as square and cubic measures. It is crucial to bear in mind that units of measurement do not merely represent simple numerical values. In the realm of working with units of measurement, different units need to be converted into a shared unit in order to accurately perform addition or subtraction. It is widely recognized that 12 inches is equal to 1 foot, 3 feet is equal to 1 yard, and 1,000 millimeters is equal to 1 meter. Some denominant numbers can be added the same way as whole numbers, but the units of measurement must always be considered. Remember to always perform calculations on numbers of the same denomination. Let's examine an example to illustrate this point. Pay attention to how the units of feet are arranged in one column, while the inches are presented in a separate column. By adding the feet and inches individually, we can determine the respective totals for each denomination. An alternative method for adding the two denominant numbers is to first convert all measurements to inches. By identifying the smallest common unit between the two measurements, we can also minimize the use of fractions. It is recommended to state the answer to problems involving denominant numbers in the original units. In other words, if the problem was presented in feet and inches, it is best to express the answer in feet and inches. Denominant numbers are multiplied to calculate the area of a surface. In the case of determining the area of a shape using feet and inches, it is important to express the answer in square units. A square is a geometric figure characterized by 4 sides of equal length and corners forming 90-degree angles. A square foot represents a geometric figure where each side measures precisely 1 foot. Let's consider a practical example of calculating the area of a small slab, which forms a rectangle with one side measuring 9 feet and the other side measuring 6 feet. Since both measurements are expressed in the same unit, we can directly multiply the two measurements to obtain the area. The resulting answer should be stated in square feet, as no conversion to a different unit is required. To verify the accuracy of this calculation, a proof can be constructed through an illustration. Each small box within the illustration represents 1 square foot. By counting the number of small squares, we can confirm that there are indeed 54 of them. This visual confirmation provides evidence that the initial calculation is correct. At times, it is necessary to determine the area even when the side measurements are expressed in different units of measure. When tackling a problem that involves varying denominations, it is typically more advantageous in the craft worker's practice to express the answer in the larger denomination. When dividing denominant numbers, it is crucial to ensure that the units are the same. When confronted with a division of two values with different denominations, the preferred approach is to convert them to the smaller denomination. Let's consider an example problem to illustrate this. To solve this particular problem, we need to convert the measurement of 6 feet into inches and then add the 6 inches to the total. In instances where the answer contains 12 inches or more, it is recommended to convert the answer to feet and inches. To achieve this, divide the answer by 12, which corresponds to the number of inches in 1 foot. Then express any remaining amount as inches, similar to the previous addition example. In this particular calculation, the answer would be 3 feet and 3 inches. In construction terms, the size of a surface is always expressed in square units. When we're dealing with measurements in feet, we state the area in square feet. Now, when we talk about a two-dimensional object, we refer to its length and width. These two dimensions establish the boundaries of a surface or area. So to find the area of a two-dimensional surface, we multiply its length by its width. This example shows how to first calculate an area measured in centimeters and then how to convert that answer to square inches. First, determine the area in square centimeters. A square centimeter represents 0.155 inches squared. So if you multiply the area by this conversion factor, you'll get the answer in square inches. It is important to note that all square units are represented with an exponent of 2, such as 1200 centimeters squared and 186 inches squared. To figure out how much plastic sheeting is required to cover a slab while it's being cured, construction workers need to find the surface area of the slab. Not all concrete placements are square or rectangular. Various other shapes are formed, and they are frequently combined in one placement. The formula used to determine the area of a circle is area equals pi times r squared. The pi symbol always represents the same value, 3.14. This number is the rounded off value, which usually does the job for calculations involving concrete. The letter r in the circle's area formula represents the radius, which is the distance from the circle's center to its edge. Basically, it's precisely half of the circle's diameter. To find the area of a circle, all you need is the radius. Section 1.5, 3 area of triangles with no known height. At times, we don't have the altitude or height of a triangle at our disposal. No worries though. If we know the lengths of all 3 sides, we can still crunch the numbers and find the area. Step 1. Add up the measurements of the sides, then divide the sum by 2. Step 2. Calculate the difference between this result and the length of each side. Step 3. Multiply all 4 numbers together. Step 4. Now whip out the trusty calculator, take the square root of this result, and voila! You've got the area of the triangle. It is often necessary to know the volume of a 3-dimensional shape, especially when it comes to calculating the volume of concrete needed to fill it. 3-dimensional shapes have 3 dimensions: length, width, and height. The interior volume of a 3-dimensional object is always stated in cubic units, such as cubic feet or cubic inches. The volume of a simple cube or rectangular prism is equal to its length times its width times its height. Remember, however, that the denominators must all be in the same units. Let's take a concrete form that is 1 yard long, 23 inches wide, and 18 inches high. Now, we need to figure out the volume of the form, but in good old cubic feet. Here's how we tackle it. Start with the formula. Volume equals 1 yard multiplied by 23 inches multiplied by 18 inches. To get an accurate volume, we got to have all the measurements in the same units, so convert everything to inches. Since we know that 1 yard equals 36 inches, we can rewrite the formula like this. Volume equals 36 inches by 23 inches by 18 inches. The volume comes out to be 14,904 cubic inches. If we want to switch from cubic inches to cubic feet, just divide those cubic inches by 1728, and bam, you've got the volume in cubic feet. In this case, the volume comes out to be 8.63 cubic feet.
Our objectives for today are:
1. We need to be able to identify parts of construction drawings. 2. We need to be able to explain how to prepare a takeoff. Lastly, we need to be able to explain how to calculate concrete volume for specific structures. Architectural, civil, mechanical, and electrical plans are all included in the documentation package for a commercial building. Each set of plans will include separate plot plans, foundation plans, floor plans, elevation drawings, section drawings, and detailed drawings. It's important to be able to understand the lines and symbols used in each plan in order to accurately interpret the information. Property lines show the boundary of the property where the work is occurring. All work should take place within the property lines. Main object lines are used to outline the visible elements on the plan, such as walls, doors, windows, roofs, and foundations. Hidden lines represent objects that are not visible, such as a foundation below a floor. Center lines go through the center of symmetrical objects, make it easier to find objects on the drawings, and help with dimensioning. Dimension lines either mark the size of an object or show the distance between objects. It's important to note that these lines include the dimension value and extension lines that project out from a particular point on the specified objects. Section lines show an object has been sectioned, meaning a virtual slice has been taken through the object to create a new view. Reference lines contain letters and numbers at the ends of section lines that refer to the related detailed drawings. Long break lines indicate a disconnection on the plane but not on the item. Long break lines show items that cover longer distances than are possible to show given the scale of the drawing. Short break lines show where part of an object is removed to reveal a hidden feature such as part of a wall removed to show the studs. Leader lines connect text with the subject to which it is related. It's important to note that drawing lines and symbols are not standardized. So be sure to check the legend on the drawings for information about the use of a particular line style on a drawing. Symbols and abbreviations are used to conserve space in a drawing set. Some symbols will look like the object they represent, while others will not. Workers tend to use or recognize common symbols. Again, remember that symbols can vary from company to company. The drawing legend should always be consulted when there is any doubt about an abbreviation or symbol. Construction drawing sets should always have one or more legends. The table on this slide shows examples of symbols for common building materials. Note that concrete and structural steel have their own symbols. Some symbols look alike, so it is important to evaluate the surrounding components carefully. The figure on this slide shows commonly used piping symbols and abbreviations. There are a wide variety of plumbing fixture symbols. In commercial construction, water piping and drains must often penetrate concrete slabs and walls. It is important to check all concrete structural elements for required embedments or inserts for outlets and drains, and to ensure any rough-in and forming work that needs to be completed before placement has been done. Each drawing uses a specific scale to represent distances on the project. It is important to check the scale because it will vary from drawing to drawing, and sometimes a single sheet will use separate scales. You can use dimensions to determine how large an object is and its location relative to other objects. Use the information on the drawing to calculate a particular dimension. For a variety of reasons, you may not get accurate dimensions if you measure the drawing itself. You should use the dimensions to check all measurements for each concrete wall or slab under construction. Contact your supervisor if there are any errors. Any changes that occur after the plans have been approved are considered revisions. Anytime there is a change, there will be a revised dated plan sheet. You can check the project documentation to determine if the version of the plan you have is the current version. Tables of important information about mechanical equipment, finishes, and components are referred to as schedules. Schedules use letters and numbers inside a circle or triangle to identify each item. Your working drawings are your blueprints. You will find the general layout and information from the surveyor on the plot plans. Items like foundation plans and schedules are in the architectural and engineering drawing, and any details for custom features or unusual designs will be in the mechanical, plumbing, electrical, and ductwork drawings. The most important plans for slab construction are the plot plan, foundation plan, site, and underground utility drawings, along with the relevant section and detail drawings. The plot plan positions the project in relation to the property lines. You can use this plan to find information about utilities, site dimensions, sidewalks, driveways, and retaining walls. It also contains a compass, contour lines, and benchmark elevations. You can find information about the foundation and internal partitions on the foundation plan. Because the footings are below the slab, these are depicted with dashed lines. The footings extend beyond the boundaries of the slab and distribute the weight of the structure to the soil. Use this plan to find information about the locations of studs, piers, and columns. You can find information about walls, doors, windows, patios, walks, stacks, fireplaces, built-in cabinets, and appliances on the floor plan. This plan shows a cross-sectional view taken horizontally between the floor and the ceiling. Elevation drawings show each exterior side of a building. The elevation drawings include windows, doors, chimney, and roof lines. For additional details on cabinets, bookshelves, and fireplaces, check for interior elevation drawings. Check the section drawings for information about items that cannot be easily seen on other drawings, such as walls or stairs. To reduce errors in plan interpretation, it's important to have a routine to follow for your construction drawing reviews. First, review all architectural symbols. Next, read all the notes in the drawings. Then review all the line symbols and dimension markings. Use calculations to check detailed dimensions against the overall size of the structure. Make a mental list of the basic construction procedures you need to build the structure. Doing this can help you determine whether any items were left out from the drawings. Finally, check the plans to make sure you have the latest versions. During the takeoff process, use the information in the plans and working drawings to estimate the amount of concrete needed for the project. There are software packages that will assist with this process. Site preparation, formwork, labor, equipment, reinforcement, concrete, and taxes are all part of the cost of a project. Some of these costs can change between the time the estimate is made and the placement occurs. Math and plan reading skills are critical to accurately estimating concrete quantities. To ensure your estimate of the amount of concrete needed is accurate, use a procedure. First, locate and make a list of each of the structural elements you will build with concrete. Then use the dimensions of each concrete element to calculate the volume in cubic yards. Use the working drawings to determine what items are to be built of concrete, such as footings, columns, slabs, foundation walls, stairs, sidewalks, and curbs. You can find these items pictured on the plans, scaled on the detail sheets, and listed on the schedules. Thoroughly review the drawings and schedules, noting each item to be constructed with concrete. There may be 5 foundations that are the same size. Count each one separately and document the dimensions in a spreadsheet. List similar items together in the spreadsheet. Use of a process like this will reduce the likelihood of concrete structures being overlooked. For concrete placed on the ground or in forms, there's usually a 5% allowance for waste in the estimate. The allowance anticipates accidental spillage from deflection and slight differences in the thicknesses of a slab. It's better to overestimate the amount of concrete needed than it is to underestimate. The formula for column and box footings is the same as it is for a slab. Volume equals length times width times depth. Because there are separate placements for column and box footings, these items are estimated separately, which make them easy to overlook when reviewing the plans. Wall footings are spread footings placed on grade. In certain situations, these are constructed with keyways to provide additional lateral strength for the base plate of the wall above. Use the dimensions of the keyway to calculate its volume and subtract it from the concrete volume of the footing. This assumes that the keyway has parallel sides. If it does not, the difference in volume will be so small it won't matter. When estimating concrete quantities, measure concrete walls to the nearest fraction of an inch for width and to the nearest inch for height. It's important to subtract openings for doors and windows from the wall volume. A slab is a thin rectangular solid. Because of differences in labor costs and formwork, you should prepare separate estimates for slabs on grade, elevated slabs, and topping slabs. When there is a corrugated support structure, the corrugated metal formwork is left in position after the concrete is placed. So the thickness of the floor is identified on the drawings as the distance from the top of the corrugations to the floor surface. Because concrete must fill the valleys of the corrugations, using that dimension for a volume estimate does not accurately capture the concrete volume required. This is the distance D1 in the figure. So, in order to calculate the concrete volume in this situation, use the total depth of the bottom of the corrugations. Stairs are cast in place against either the ground or shoring. Treads are the horizontal parts of the stair. Risers are the vertical parts. Only the vertical parts of formed concrete stairs and the ends of the stairway need forms. There is 1 cubic foot of concrete for each linear foot of riser. So if a stairway has 8 risers that are 4 feet long, the volume of the concrete is 32 feet. Use the formula for a rectangular solid when estimating a straight curb. When estimating a curb and gutter, use the formula for 2 rectangular solids and add the volumes together. Some manufacturers of curb or curb with gutter forms provide a concrete factor for each lineal foot of form to assist in estimating. It's important to calculate the volumes for freestanding columns according to their shapes. For rectangular columns, use the same formula used for box footings. For round columns, use the formula volume equals pi r squared times height, where r is the radius and h is the height of the column. For other shapes, you have to calculate the area of the cross-section of a column and then multiply it by the height. Every operation needs a hazard analysis during a team huddle before we start. Thanks for watching, and remember, you are the key to our company's success and safety. See you out there on site.